So first I start by giving you the general structure of a quantum computation. What it is generally about is it is actually quite a giant multi-slit interferometer. That's what quantum computation is. Okay, so typically you start with a particular state of a system, right? We can call this, we'll typically call this 0, okay, and then there are states which are 0, 1, 2, dot 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 capital N minus 1, okay. These are like capital N slits, okay. So first what you do at the start of quantum computation is transformation, okay, and this transformation is known to us. It is a very simple transformation. It's called the Hadamard transform, which is just a Hadamard operation on each qubit separately, okay. That's what the operation you do, and that's a simple way to create a giant superposition, okay. Why I'm calling it giant, okay, because you see the simplicity of this. You just have small n qubits, okay, each initially in this state 0, okay. So this is 0, 0, 0, 0, and all you do is Hadamard operation on each of these n qubits, okay. So you end up with 1 by root 2, 0 plus 1, yeah, and whole to the power n, okay. And as you can see, that thing is nothing but this is a classic starting state of quantum computation. I will call this the starting state of quantum computation, this equal superposition, okay, because this is the operation which you always do. From zeros you go to so this thing, when you do Hadamard, just they have just n qubits sitting next to each other, and you just do Hadamard on each of them. It's a dead easy thing to do, but you see it has everything, okay. 0 plus 1 will, this is equal to 1 by 2 to the power n by 2 summation over x, okay. So actually let me write one more step here for your convenience. 0, 1, 1, 1, okay, which is nothing but summation over x equal to 0 to capital N minus 1, 1 by root capital N x, okay. So though I have written this at the bottom of the board here, okay, this state, which I'll just label as psi, is a very important state. We start almost all quantum computation from that state. It's an equal superposition of everything, and the interesting thing is, if you were trying to do this with an actual particle, say for example, okay, this capital N is in quantum computation notation, capital N is 2 to the power small n, where small n is the number of qubits, okay. So it's huge, it's gigantic, okay, but it's dead easy to create this equal superposition because you do Hadamard on everything, okay, and that's usually done as the first step in any quantum computation. Then yeah, yeah, it's very easy. Hadamard is just a rotation of 0 to 0 plus 1 and 1 to 0 minus 1, okay. So it requires some kind of rotation about one axis and then another operation. It's not exactly half a rotation, because no. So okay, so what you do is, say you have a state 0, 0 is like the state up in the block sphere, okay. Then you apply half a rotation about, say, y axis, okay, and then you also apply y another x rotation or z rotations. You do another extra one as well, okay. So it's not just half a rotation will have a factor of I. You eliminate that. So it's you do 2 rotations about 2 axes, and that's the Hadamard. And for that you apply magnetic fields. Yeah, you can think if it's a spin qubit, you just apply magnetic field to let it precess, but you require 2 rotations. And Hadamard is just a basis changer. It changes from z basis to x basis and vice versa. It's its own inverse, okay. It's a composition of 2 rotations. So it's very easy. It's the most, is kind of the first operation anyone does on a qubit, okay. And you do that individually, okay, and you have created this giant superposition. Okay. Now, quantum computation is its interferometric pattern where the problem is encoded in these phases. So, this is of course human ingenuity if you can cleverly encode your given problem on these phases. Okay. So, you encode in these phases. Moreover, application of these phases to these qubits must be relatively easily done. Okay. So, that is one criteria. And then you do another transform. Okay. This is often the Hadamard transform, but in some cases it's the quantum Fourier transform. Okay. In other cases it may be just operations which you are kind of variationally seeking what to do. Okay. But in the end what happens is you bring okay. So, this is one has to be a bit careful. It's not really a spatial interferometry as you would do with a particle, because it's discrete. So, only n-1 alternatives they mix and interfere, and then you measure the answer whether it's finally it's 0 or 1 or 2. Okay. And essentially that gives you the answer to the quantum computation. Okay. So, quantum computation is a giant interference. Okay. Oh, so C naughts are not in this picture, not visible, because I have kind of labeled everything as a so this capital N minus 1 state is all one state of many qubits. So, C naughts will be inherent in the operations that you need, for example, to encode these phases, okay, or to understand these or to do these transforms. So, if it's not a Hadamard transform, then you will also need C naughts to do some, if you want to do a quantum Fourier transform. Okay. So, those come, yeah.
But Hadamard was a single qubit gate.
Yeah.
C naught will be a 2-qubit gate.
Right. Bring, yeah. So, that may be needed for some transforms, not for the Hadamard transform. So, those problems which you solve by the Hadamard transform, for this part you do not require a C naught, for example. But to encode the problem, these phases, you see this phase phi naught is given to the all zeros. The second phase phi 1 is given to the all 0 plus 1 at the end 1. So, they require information of all the qubits. So, in general, to give that phase you need some C naughts. Okay. So, I am not talking about it in the qubit space now, I am just giving the physical picture of what a quantum computation does. Okay. Sometimes you may need to iterate this, you do it once, okay, then you do it again and again and again. Sometimes you may measure, okay, and get some outcome, then repeat the whole process. Okay. But overall it is just a giant interference. Okay. And the ability to produce this initial state psi, which is superposition of every state, the exponential number of states, okay, is what helps the thing. Not yet. So, that is the state here. This is the psi. This state where you have created this equal superposition, that is the state psi, and I will take that as the starting state of all quantum computation. So, I will start from here. Okay. I will not think of, because this is an operation you always do. Okay. So, you start from here and then you see how you encode problems. Okay. So, the earliest illustration always is the simplest of algorithms, which is a single qubit algorithm, which is the Deutsch algorithm. But before that I need to convince you a little bit about something, is that how to, yeah.
What you did after assigning, first you got an equal superposition of these states.
Correct.
Perform some operations involving C naught or anything.
Yeah, to encode the problem through phases. Okay.
You got phases assigned to each sort of superposition states.
Mm-hmm.
And after that, what did you do?
After that, we do another transform, which is the interferometry. So, essentially it can be a repeat of that Hadamard transform. For some of the illustrative algorithms this works. These are kind of toy algorithms. For the useful ones, okay, you may, one of the useful ones, you use a quantum Fourier transform, for which you also require C naughts. Okay. But essentially something which mixes all the paths with all the other paths. Okay. That kind of matrix. Okay. So, and then it's again that operation has to be simple enough, require few enough something which is in like power law in the number of C naughts or things, not exponential, okay, for it to be a useful one. And that is the ingenuity of the person who comes up with the algorithm. The problem encoding must be simple, and this transform must be simple. Okay. You can input data if you want. So it is typically encoding a problem that you want to solve. So sometimes it's more often the problem than the data. But if you have no one knows a good way to encode data in quantum states yet. Yeah, but people often assume that you can.
Sort of choose something which I can completely gauge away, right? So for example, if I choose phi naught equal to 0 and phi 1 is phi, and then
Yeah.
phi 2 is 2 phi and so on, then I can kind of gauge it away, right? I can absorb that.
Right. So first of all, for example, the phi 0 is not required at all. Okay. So phi 0 I just wrote, but typically yeah, it's only from phi 1 to phi n minus 1 which is important. And of course, if it is a nice multiple, okay, then you just have one variable. Okay. So that is a problem called quantum phase estimation, that you can very naturally guess what will solve that. That is the Fourier transform, because then the phi's will give you, it will give you the momenta which are prevalent here, and after the Fourier transform, those momenta will be the outputs. Okay. So that is also there in the Shor's algorithm in some sense. Yes, I will clarify. Okay. I mean, all the algorithms are basically they are very much physics. It's just reinterpreted in the language of qubits. Yeah. Okay. Right. Yeah.
Give an example of how would I experimentally use it?
Yeah. So that will become clear when I give the actual example. So no one would actually do the picture I have done. Okay. This picture is to show you the structure of quantum algorithms. You're actually doing it in the n qubit space. You see. So on that space you will work with operations and C naughts and things. Okay, to do the quantum computation. Okay. Now, so first illustration, but before the first illustration, I should tell you one thing. Maybe that goes partly to answer your question, is that how do I encode? Say a problem could be a function. Okay, function into a phase. Okay, so that requires something called conversion. So typically functions, how do we do? So you have to have an efficient function evaluator. Okay, this is called a black box. Okay, and typical black boxes are in classical computing are x and will give you out fx. Okay. Of course, for any algorithm to really be useful, this black box must be something simple enough, right? Otherwise, it's not much. But suppose there is a black box which evaluates a function. You give in x fx. Okay. This is how our classical computer works. Okay. This is called a black box or oracle. However, you see in quantum this does not work. Okay, because two values of x, 0 and 1, could give the same value of fx. Okay, so unitary operation cannot be 2 to 1. Okay, so this is why in quantum mechanics the black box is a bit like this. You take in x, you take in a blank state, another second qubit in a state b, and what you do is you retain the x, and here you do b plus fx. Okay, so this retains all information and it's a 2 to 2 unitary. Okay, so this is called a bit query black box. Okay, so you can go back. Yeah, it's a unitarily possible thing, and that is where. So if the b is 0, you just get fx. If b is 1, you get the complement of fx. Okay, so that keeps all the things consistent. Okay, now. This is still not encoding in a function. This is still like writing on a piece of paper, right? You have written the fx, okay? Only that if the paper was, a white paper, you like fx. If it was a black paper, you write fx complement, okay? So two options for each x, okay? Now we have got to change this kind of. Yes, for the moment I assume that. Yeah, so you can do it for multi-valued ones. Then this register also has to be kind of that many possible values has to be there. Yeah, correct. That's a good question. Okay, so so first of all, you have to convert this to what is called a